Welcome to a read along with Dr. Powell. In the book Discrete Perspectives in Mathematics, this is subsection 5.4.2, Mobius and power sets. Okay, so let's remind ourselves what we talked about in the last subsection. We talked about a Mobius map or a Mobius matrix, which describes that map or function that goes from Z4, meaning tuples of integers with four things in it, to tuples of integers, four things in it. So it's the codomain is Z4 and the domain is Z4 as well. And so these are free Z modules, and the map between them is can be given by a matrix, since it's a Z module map between free Z modules. And it's a solving map here. It solves the summand problem. Given cumulative sums at these nodes, we end up getting summands at these nodes. So that up to 1, let's see, -3 and 4 as summands add together to give you 1. And 2 right here, everything below it, including it. So this point, this one, this one, this one, all added together should give you back to 2, which it does. So we have a solving problem. Now let's take a look at this in relation to power sets and the poset structure on a power set. All right. And the Mobius map or matrix, which is associated with it. There's a lot of things that we can do here because of symmetry within the poset of a power set, where the ordering is based on inclusion of subsets. Okay, so we can partition a power set by setting up different categories. All right. Basically, pretty much C0, this category is just has the empty set in it. We're just kind of dividing up the power sets, or the subsets of a set, so the different elements of a power set. So C0, let's suppose that that's just the empty set. C1, let's suppose that's all the subsets that just have one element in them. C2, subsets that just have two elements. C3, the ones that just have three. Okay, how many do we have in each one? Well, let's suppose that our initial set that we're taking a power set of is has three elements in it. Okay, so we have three things to choose from to make a subset of size 1, subset of size 2, and a subset of size 3. Hence these binomial coefficients, because we have three things to choose from. And how many ways that they're choosing nothing? Well, 1, that gives you the empty set. How many ways that they were choosing just a singleton set? There are 3. For instance, if we just had three elements here, such as A, B, C, then the different singleton sets are A, B, C. The sets of size 2 are A, B, A, C, and B, C. So notice there's 3 of those, and there's 3 of those right there. And there's one way to get all of them together. Okay. So, all right, so let's look at this. So for instance, if we add up all the sizes of these categories, we get the number of subsets. That's because these categories partition the power set. So all subsets of S can be partitioned into these categories. All right. So if you add up all these binomial coefficients, you'll end up getting 8, as expected. Okay. Now, here's a little polynomial description of it. If we expand this using binomial coefficients, saying what they are, this is the coefficient of x to the 0, coefficient of x to the 1, and so forth. Then if we plugged in 1 into here, so we just have x as being 1, then we just get the sum of the coefficients, we end up getting 2 cubed. That's another way of saying that. Okay, we can use, those are some basic ideas, but we can use those ideas as we think about the Mobius function or Mobius map on the poset structure of a power set. Okay, all right, so we have 8 different nodes, and we're going to put them in our different categories here. There's 8 different standard basis tuples, all right, with a 1 being at a node and then zeros elsewhere. Let's see if we have some pictures of these. So here's one, for instance, and this is one of the standard basis elements. And what follows below is the description of how we solve the sum-n problem just for this particular one right here. So we want to have sums of zeros right here and a sum of 1 here. Well, obviously we have to have a 1 here. And to have zeros, we need to put negative 1. So negative 1 and 1 would be 0 here. Negative 1 and 1 would be 0 here. Negative 1 and 1 would be 0 here. Then having these right here as our sum n's, we can get the next line up by thinking of, we need zeros to appear here. So let's think about that. 1, negative 1, and negative 1, and something else have to add together right here. So everything below this node to give us 0. So this better be a 1. And similarly, by symmetry, a 1 here and 1 here. Notice that in each category, you're going to have the same solution because of how symmetric things are for the sum-n problem. So we have negative 1s here in this category. This category, we have all 1s. So we had a 1, negative 1s, 1, and up here, you're going to have a negative 1. That pattern is kind of what we're going to be seeing as we move along. In fact, you can kind of see it here. What if we take the number of things in each category and alternate the signs with a minus, plus, a minus via polynomial math? That should give us 0, which is the same thing as saying we got a 0 cumulative sum up here, is actually can be thought of via this calculation as well. Okay, so and then we can look at another one like this one right here. And if we go through the process, notice something interesting that develops. We have just in the part that lies, just in the part that lies just above this going up right here, we see a power set structure on 2 elements, and it has an alternating pattern of 1 and negative 1s and 1 right there as we go up the different levels. All right, so this is graph isomorphic to has the same structure in a poset to this Hasse diagram, right? Well, we have a Hasse diagram version of the poset of this power set on just 2 elements. Okay, notice that we have a so notice that we have the 0 at the top. So if you actually looked at, so this 0 right here, the 0 at the top can be thought of via this alternating sum of binomial coefficients as well. But we can kind of get it just by working through the ideas that we had above. Okay, so that concludes this little subsection. We're going to use these ideas in a later subsection. So coming up, even the next one, so 5.4.3, we're going to use these ideas. So please keep these in mind. Thanks for watching.